Welcome back. In this short video, we're going to keep on exploring our left-hand and right-hand limits. We're going to take a look at some more algebraic simplification of limits. We're going to take a look at graphs again, and then finally we're going to look at sandwich theorem. The sandwich theorem is the only one that I'm going to take a look at in this video in terms of an example. Most of the rest of this assignment is going to be very similar to what you've already been doing. We're going to formalize some of the properties that we use, but it's not necessarily anything new. So first of all, we have all these properties. So let's just quickly run through them. If you take the limit as x approaches a critical number of a constant, it's just that constant. Think about this as just a horizontal line. So like if I say the limit as x approaches 1 million of 1, it's just going to be 1. That's all it is. If you have the limit as x approaches a critical number of just the identity function x, it's whatever the number you're going to. This one just says that if you have a polynomial function, or if you have the limit as x approaches a critical number and you're just adding or subtracting the equations together, you can do each one of them individually. Same thing here with multiplying and then dividing, and then if you have a constant, you can pull the constant out front. You're going to see me pull constants out front a lot. These ones with powers, then we have a polynomial function, a quotient function, nth root to the whole thing, and then finally the sandwich theorem. The sandwich theorem is the one, like most of this stuff, 1 through 12 are just kind of common sense. 13 is the one that gets a little bit tricky. It just says that if you have an equation, h of x, and you can't necessarily evaluate the limit of h of x. If you could, you would do that. You can't simplify this algebraically, but if you can evaluate if h of x falls between f of x and g of x, and you know the limit of f of x is L, and you know the limit of g of x is L, then the limit of h of x also has to be L. I'm going to do one example of that so you can see it. We're going to use this a little bit later on when we take a look at derivatives of our trig functions to prove those derivatives. I'll just show you a quick example of that. So using sandwich theorem, we have the limit as x approaches 0 of x squared times the sine of 1 over x. You can't just plug in 0 because you get division by 0, so that doesn't work. But what we do know is that the sine of 1 over x has to fall between -1 and 1. It has to fall between those values. You learned back in pre-calculus that the sine has a max of 1, it has a min of -1. So if we set up this relationship right here, this is going to be my f of x, this is going to be my g of x. That's always got to be true. Then what I'm going to do is I'm going to multiply through by x squared. So I multiply through by x squared. I get negative x squared is less than or equal to x squared times the sine of 1 over x, which is less than or equal to x squared. And what you can find then is the limits on these outside equations. If I take the limit as x goes to 0 of negative x squared, that is 0. And if I take the limit as x goes to 0 of positive x squared, that's also 0. Therefore, the limit as x goes to 0 of x squared sine of 1 over x has to be 0. Has to be. Sandwich theorem guarantees that. So most of this assignment is based upon those algebraic simplifying and different things that we've been looking at already. Maybe throw in a little sandwich theorem just to, and usually we have a trig because it falls between that -1 and 1. Those are the easiest one. Okay, see you in class.